Hello, I'm Soumya Srivastav and I'm presenting today's work with my co-author Professor Nagesh Kumar Daseka. We are affiliated to the Department of Civil Engineering and the Divecha Center for Climate Change at Indian Institute of Science, Bangalore, India. The topic for today's presentation is multi-site multi-variable hydrologic model development for spatially heterogeneous river basins to achieve realistic basin modeling. This is a brief overview of my presentation. Hydrologic modeling is a process that helps us understand the various rainfall runoff processes happening in the river basin. Hydrologic modeling is based on several physical laws, and for these physical laws, there are some parameters whose values need to be optimized in order to maximize the model performance. This method is known as model calibration. The general trend is to calibrate the model for stream flow at the basin outlet. However, with the advent of remote sensing and more observed data, it only makes sense to include some more data into the calibration process, such as calibrating for stream flow at multiple locations, but also including some other hydrologic variables such as evapotranspiration, soil moisture, sediment, etc. That brings us to two scenarios. One is the multi-site calibration. The other one is multi-variable calibration. First thing is that we are making good use of whatever data is available. And secondly, this type of multi-site calibration is going to take into account the characteristics of the entire basin. Next is multi-variable calibration. With the advent of data, it makes sense to utilize all of that in the calibration process, and this is known as multi-variable calibration. So this multi-variable calibration, again, it is making full use of the field measurements, and it has also been suggested to reduce the uncertainty in parameter estimation. In this study, the following objectives are being laid out. First is that calibration and validation of SWOT, which is Soil and Water Assessment Tool model, is done using SUFI2 algorithm, which is Sequential Uncertainty Fitting Algorithm, by using SWOT cup, which is SWOT calibration and uncertainty programs. And this calibration and validation is done at multiple locations for stream flow as well as for evapotranspiration. So whatever study we have conducted, we have also done validation. However, in today's talk, I'll be showing the results of calibration. The next objective is to find out which performance measure gives good result for stream flow calibration and which gives good results for actual evapotranspiration calibration. Comparison of multi-site, simultaneous and sequential stream flow calibration is done. After that, we are comparing the stream flow calibration with stream flow plus evapotranspiration calibration. The methodology for multi-site multivariable calibration can be seen in this flow chart. We have some inputs, we feed them into the model, we set up the model, we run the model, then we calibrate the model for stream flow. Here we had stream flow data for 23 locations. We calibrate the model for evapotranspiration. If we get satisfactory calibration results, then calibration is complete, model validation is carried out. If results are satisfactory, then we are done with the process. For the present study, our area of research is the Mahanadi River Basin in India. Here the river basin area is 1,42,000 square kilometers. The number of sub-basins are 54. These are some of the input data that I have used. These are the various calibration scenarios that have been studied here. First is single site. So calibration is being done at a single site for stream flow. Then second is multi-site simultaneous. So for all the 23 locations, I am simultaneously calibrating the model for stream flow. Next is multi-site sequential. Here sequentially the stream flow calibration is being done for the 23 stations. And the last is multi-variable calibration. So here we are including stream flow as well as evapotranspiration for the calibration process. First study talks about the choice of performance measure for stream flow calibration. Here, streamflow calibration has been done at the most downstream outlet for which data was available, which is outlet number 27. We have used different performance measures like Nash-Sutcliffe efficiency, coefficient of determination, percent bias, and Kling-Gupta efficiency. So this is a box plot for the streamflow at outlet 27 in different calibration scenarios. Calibration is done only at outlet 27 for streamflow only. We see that the spread of the observed data is less, but if we talk about the simulated data for all these 4 scenarios, the spread is much greater than that of the observed data. Second thing that we can see here is that if we talk about R square is able to capture the median of the observed data well. But if we talk about high flows, then R square is not simulating well for high flows. In fact, when we are using R square as a performance measure, the high flows, the peak flows are being overestimated. The cyan line, it shows R square. So if we talk about the low flow periods, it seems that R square is capturing this low flows very well. While R square is capturing the stream flow well for low flow periods, whereas percent bias is working well for high flow periods. First of all, we see this red block. Red means calibration is being done for Nash-Sutcliffe efficiency. Now, if calibration is being done for Nash-Sutcliffe efficiency, we can see that the value of R square is also high, the value of NSE is also high, and the value of Kling-Gupta efficiency is also slightly better. Therefore, we can say that when calibration is done by taking NSE as the performance measure, then even R square or Kling-Gupta efficiency, they are showing good results. Let us move on to see which performance measures are more suited when we are calibrating the model for actual evapotranspiration. For actual evapotranspiration, we see that the spread of the data for different simulation techniques, it is almost the same as that of the observed data. And here, if we see this NSE as performance measure or percent bias as performance measure, we can see that they are actually capturing the evapotranspiration of the subbasin pretty well. Here, we have plotted the actual evapotranspiration for different scenarios for subbasin 27, and we see the NSE line, we see that NSE is capturing the actual evapotranspiration well for low flow periods also, as well as for the high flow periods. Here, the calibration of actual evapotranspiration is done at 40 subbasins, and the results of subbasin 27 have been shown in the graph. When calibration is done for NSE, then the values of R square, NSE, as well as Kling-Gupta efficiency are reasonably high. That is why when NSE is taken as the performance measure, then the other performance measures are also showing good value. Then we go on to multi-site sequential calibration scenario. Here, the outlets are calibrated for streamflow based on their stream orders. The first order stream is calibrated first, then second order, and we have 8 orders of streams in the river basin. So this calibration has been done in a sequential stepwise manner. If we try to calibrate for all the stations at once, then at the basin outlet we may get a good result, but then we cannot actually ensure that even for the upstream stations our model is performing well or not. But if we do this sequential calibration, we can get optimal parameter sets separately for different stations. So this is the order of streamflow calibration for different streams. The streams shown in red are of first order, so they have been calibrated first. Then we move on to the second order stream, then third order, and so on. These are the results of this sequential streamflow calibration for different subbasins. We can see that R square values are good for most of the stations apart from station 8, and NSE values are also showing pretty good results. They are close to 1. Of course, for a few subbasins, NSE values are coming out to be negative. But on the whole, these results are generally in the acceptable range where R square and NSE both are above 0.5. Then we see multi-site simultaneous calibration scenario. Here 23 outlets are simultaneously calibrated for stream flow. So the advantage of this is that it is saving us a lot of calibration effort because we get the calibrated parameter set at once in one go. Now here I have tried to compare the sequential and simultaneous calibration. In the first diagram, we see that R square value for multi-site sequential as well as simultaneous calibration, they are very much comparable. In fact, they are almost the same in all these different subbasins. Whereas, if we talk about the comparison of NSE values for multi-site sequential and simultaneous calibration at outlet 27, of course, then we see that multi-site simultaneous calibration, that is when we are calibrating at 23 locations at once, we are not getting good results. At many places the results are poorer than what we are getting in multi-site sequential calibration. This means NSE is usually used because it captures the peaks very well. So from here we can say that sequential calibration is capturing the peaks better than the simultaneous stream flow calibration. Then here again we are trying to compare both of them, sequential calibration and simultaneous calibration. So in this graph, sequential is shown in green and simultaneous is shown in cyan or blue color. Here we see that for the low flow periods, we are getting good result from simultaneous calibration. However, for the peak flows, simultaneous calibration is overestimating the peak flows. But if we see sequential calibration is performing well for the peak flows, but it is not performing well for the low flows. The low flows are being highly overestimated when we are going for sequential calibration. Then we have the multi-variable calibration scenario. Here both streamflow and evapotranspiration are used for model calibration. First of all, model calibration is done at a single outlet and evapotranspiration is done at 40 subbasins. And in the second case, calibration of streamflow is done at 23 outlets simultaneously and evapotranspiration is done at 40 subbasins. This is the model result that we get. And here we see that when we are also adding actual evapotranspiration in the calibration process, the results are pretty much the same as what we were getting when we were calibrating for stream flow alone. So here addition of evapotranspiration is not giving us much benefit because the results are the same as when we were calibrating for stream flow alone. Here we can see then the simulated SWOT stream flow and then the simulated stream flow for these four scenarios that we had considered. Here we can see that if we talk about high flows are being well captured by the multi-site sequential calibration scheme. So these are some of the key findings of this study. For stream flow calibration, R square captures the stream flow well for low flow periods. Percentage bias works well for high flow periods. Then for actual evapotranspiration calibration, use of Nash-Sutcliffe and percentage bias helps in realistic calibration of actual evapotranspiration. Then Nash-Sutcliffe efficiency captures the actual evapotranspiration well, both for low evapotranspiration as well as for high evapotranspiration periods. Next, when we calibrate for stream flow or actual evapotranspiration and we use NSE as performance measure, then the values of other performance measures like R square, kg, etc. also increases. They are better. Next thing is that multi-site sequential calibration captures the peaks better than simultaneous calibration. Sequential calibration is capturing the peaks well, but it is overestimating the low flows. Whereas simultaneous calibration, it is capturing the low flows well, but it is overestimating the peak flows. Then we added another new variable, evapotranspiration, in the calibration process, but it did not alter the calibration result very much. These are some of the references. And thank you for your attention. If you have any queries, you can always write to us at soumya@iisc.ac.in or nagesh@iisc.ac.in. Thank you. Have a nice day.